Hello dear friends, welcome to the lecture of series of real numbers. In this lecture we shall study alternating series, meaning of alternating series, and we shall prove a theorem related to convergence of alternating series. And then we will solve one problem on it. Here I have written the meaning of alternating series, which is simple to understand. An alternating series is an infinite series whose terms alternate in sign. That means positive, negative, and so on. So, for example, the first series I have written here is 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 and so on. The second is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus so on. So, these are the examples of alternating series, and these series can be written in this form. An alternating series may be written in the form summation n takes value 1 to infinity minus 1 to the power n plus 1. So, this term is for the alternating sign plus 1 minus 1 plus 1 minus 1 into an, where each an is positive. This term an is positive or non-negative term, and this term represent the sign. So, if the first term is positive, then this will be if you put n is equal to 1, then minus 1 to the power 1 plus 1 means 2, minus 1 square is positive plus 1, and there into an, that is a1. This is first term. If the first term is negative, if the series may have the first term negative. So, for example, if the series is say minus 2 plus 4 minus 6 plus 8 etc. This is also an alternating series, and this can be written as summation n takes value 1 to infinity minus 1 to the power n, because the first term is negative. If the first term is positive, we write minus 1 to the power n plus 1. an, and an here is even, so we can write it as 2n. So, that means this term may be written as minus 1 to the power n plus 1 or minus 1 to the power n. That depends on the sign of the first term. So, generally we denote the alternating series in this form: summation minus 1 to the power n plus 1 into an, where an is positive. Now, we shall prove a theorem relating to the convergence of this series. The theorem is theorem number 7. If an is a sequence of positive numbers, if an is separated, then that will form a sequence of positive numbers such that a1 is greater than or equal to a2 is greater than or equal to a3 and so on. In general, an is greater than or equal to an plus 1 and so on. And this means the sequence is non-decreasing. The sequence is non-increasing. The first term is greater than or equal to the second term is greater than or equal to the third term. That means the sequence actually is decreasing, but instead of decreasing we use the word non-increasing. So, that is an is non-increasing sequence, and second condition is limit of an, limit of its nth term is 0. Then the alternating series, that is we have seen in this notation, summation n takes value 1 to infinity minus 1 to the power n plus 1 into an is convergent. So, this is the important theorem about the convergence of alternating series. If these two conditions are satisfied, that means the sequence is non-increasing, or in other way, simple way, decreasing, and limit of its nth term is 0, then this alternating series becomes convergent. Now, we shall prove the theorem. We will first write what will be the terms of this sequence, this series, infinite series, alternating series. The alternating series is summation n takes value 1 to infinity minus 1 to the power n plus 1 into an is equal to, see, if put n is equal to 1, the first term is minus 1 square, that is plus positive, and a1. So, it is a1. The next term will be minus 1 cube, and that is negative a2, and next will be positive. So a1 minus a2 plus a3 minus a4 and plus so on, and in general the general term is minus 1 to the power n plus 1 an and plus or minus so on. That depends on this sign, whether it is if it is positive, then this will be negative, etc. So thus this is the alternating series. Now when this series will be convergent, this series is convergent if the sequence of its partial sum is convergent. By definition, the series is convergent if its sequence Sn of, we denote the sequence of partial sum, Sn of partial sums is convergent. And but what is Sn? Where Sn is sequence of partials, sum of first n terms, and that will be Sn is equal to. From this we can collect first n terms, and sum of these first n terms will be a1 minus a2 plus a3 and minus so on, and the last term is minus 1 to the power n plus 1 an. So this is Sn, and if this Sn is convergent, then the series will be convergent. Now we shall prove the Sn subsequence of this Sn are convergent, converges to the same limit. So we shall prove the subsequences Sn S2n minus 1 with odd index, S takes value 1 to infinity, and even index S2n, n takes value 1 to infinity of Sn are or these will converge to the same limit. We shall prove that the subsequences of this sequence Sn, that is S2n minus 1 and S2n, converge to the same limit. First consider this subsequence. First consider the subsequence with odd index. These are two subsequences with odd and even index. That is S2n minus 1, n takes value 1 to infinity, which is, now we can see easily what will be this these terms of this subsequence. For n is 1, that the term is S1. N is 2, this is 2 into 2 minus 1 means S3, and S5 and so on. So this is the sequence, subsequence. Now what is S1? S1 means sum of only the first term. First term is, see this, the first term, S1. S1 is A1. And what is S2? S2 will be first sum of first two terms, that is A1 minus A2. But S2 we are not considering, we have to consider S3. The terms, this sequence is with odd index terms, and therefore the first term is S1, which is A1. Now next is S3. S3 means sum of first three terms, that is A1 minus A2 plus A3. A1 minus A2 plus A3. And this we can write, what is A1? A1 is S1. So So this is S1 minus A2 plus A3. And now we will compare this term with S1. Now we see A2 is greater than or equal to A3. So this is the first condition. Now we will use the conditions in the theorem. This sequence is non-increasing, that means A1 is greater than A or equal to A2 is greater than or equal to A3. So this term numerically it is greater than A2 is greater than or equal to A3, or simply we say A2 is greater than A3, but it is with negative sign, and therefore the sum of this minus A2 plus A3 will be negative, or that is less than or equal to 0, and therefore this quantity will become less than S1, because this is negative. A2 is greater than or equal to A3, and thus this is less than or equal to S1. Since the reason can be written as, since by A, this condition A2 is greater than or equal to A3. And similarly we have S5 is equal to S3, then the first sum of first three terms, that is S3, then fourth term, that is minus A4. We should note that here the even index terms are negative, minus A2, minus A4, minus A6, and odd index terms are positive, A1 plus A2 plus A5, etc. So therefore this, so we will collect three terms here and write it as S3, sum of first three terms, minus A4 and then plus A5. So this because A4 is greater than or equal to A5 numerical value, so this quantity becomes negative, and therefore this S3 minus some negative quantity will be less than or equal to S3. And in general, and so we will consider S2n plus 1, and this can be written as S2n minus 1. Sum of first 2n plus 1 terms we shall consider, and that can be written as sum of first 2n minus 1 term, and next is 2nth term. 2nth term is even indexed, and that is negative, minus A2n, from this you can see, and next will be 2n, and next is negative, next is with odd index, and that will be positive, that is plus A2n plus 1. See, like this we have written S5, S3 minus A4 plus A5. Here S2n plus 1, sum of first 2n minus 1 terms, then 2nth term which is negative, and 2n plus 1th term which is positive. Again numerical value of this is greater than or equal to this one, and therefore this quantity becomes negative. So it is similar to this, that is minus 7 plus 5, and that is negative because 7 is greater than 5, and that the same thing is here in these relations, and therefore this is less than or equal to S2n minus 1, and thus we have thus we have the relations in the terms, subsequence S1, S3, S5, etc. Now see the first, S3 is less than or equal to S1, means S1 is greater than or equal to S3, and here S5 is less than or equal to S3 means S3 is greater than or equal to S5, and that continues greater than or equal to. In general, this is S2n minus 1 is greater than or equal to S2n plus 1. And that continues. So what this shows, this sequence Sn, S2n minus 1, odd index, this sequence S2n minus 1 is non-increasing sequence. Therefore, the sequence s to n minus 1, n takes value 1 to infinity, is non-increasing. Now we will again form the term s to n minus 1. Now here we should note that the terms even index terms are positive and odd even index terms are negative and odd index terms are positive in this Sn or in the alternating series. Also, what will be s to n minus 1? This we shall write. Sum of first 2n minus 1 terms. We will start with a1. So, a1 minus a2 and we will write in brackets a1 minus a2 plus a3 minus a4. The terms are like this: a1 minus a2 plus a3 minus a4 and so on. And see, the last is a2n minus 1, but before that the earlier bracket will contain a2n minus 3 minus a2n minus so see the terms minus 2 and plus a2n minus 1. These are the terms in serial order. So, first 2n minus 1 terms we have written, but we have grouped the terms, first 2 terms and next 2 terms and so on. So, why we have done this? Because we want to decide whether it what is this quantity, positive or negative, or what is the relation for this one. Now, a1 you see the bracket a1 minus a2, this a1 is greater than or equal to a2, and therefore, because a1 is greater than or equal to a2, this quantity is non-negative. If they are equal, then that will be 0, but it will not be negative, or if a1 is strictly greater than a2, then this is positive. So, either 0 or positive, and therefore, we use the word non-negative. So, this quantity is non-negative. Similarly, this is non-negative, same relation holds because of a. And last a2n minus 1. a2n minus 1 is the term in alternating series, and that is non-negative also, because sign is separated in the notation of this series. This sign represents either plus 1 or minus 1. This term represent either plus 1 or minus 1, and this an is non-negative, or generally it is positive, and last term is positive. That means each bracket term is non-negative and the last is positive, and therefore, this quantity is certainly greater than 0. So, that we shall write the quantity in each bracket by 1 by this condition 1, or by the hypothesis 1. That is 1 means a, first a, hypothesis a, each quantity in the brackets is non-negative. Each is non-negative, and the last is a2n minus 1, that is positive by definition of alternating series. Each term is positive and its sign is considered separate, so it alternates. So, therefore, what about s2n minus 1? That becomes greater than 0. So, each quantity is non-negative and the last is positive, means positive means greater than 0, and therefore, s2n minus 1 is greater than 0 for all n belongs to n. And what this shows, therefore, the sequence is bounded below. All the terms are greater than 0, means all the terms of this sequence s2n minus 1 are positive, and therefore, the sequence is bounded below and this is lower bound. Therefore, s2n minus 1, n takes value 1 to infinity, is bounded below. Now see, what we have proved here earlier, the sequence is non-increasing. It is non-increasing, and we have further shown it is bounded below. And we know a non-increasing sequence, that means actually decreasing sequence, but it is bounded below, is convergent. This is a theorem that we have studied in chapter of sequences. So you please refer that theorem. The sequence which is non-increasing and bounded below is convergent. Similarly, the sequence which is non-decreasing and bounded above is also convergent. That we will use for the second subsequence. So thus Sn S2n minus 1, n takes value from 1 to infinity, is convergent. Now consider the subsequence with even index. Next, even index, and that subsequence we have written S2n. n takes value 1 to infinity, which is you can see here S2, even index, first term. N is 1, it is S2. N is 2, it is the term is S4, S6, and so on. So this subsequence we shall consider, and here we will write directly what is the S2n plus 1 term. So we have S2n plus 2 term, and that will be S2n, sum of first 2n terms, and next term of 2n plus 1, and that term is positive, A2n plus 1, and next term will be A2n, that is even index, and that is negative. We have seen in the series the odd index terms are positive, even index terms are negative, and therefore the sum of first 2n plus 1 terms is written as S2n, sum of 2n terms, and then 2n plus 1th term and 2nth term. So for example, if we write S12, then that can be written as S10, sum of first 12 terms here, and on the right side we will write sum of first 10 terms, and then 11th term, that is positive, A11, and next A12, which is negative. So in this way the sum is expressed, 10 terms sum plus 11th term plus 12th term, but even term is positive, even term is negative, and odd term is positive. In that way we have expressed the sum, and because this A2n plus 1 is greater than or equal to A2n by the first condition, A1 is greater than or equal to, see, one thing you should correct here is 2n plus 2. 2n plus 1 and 2n plus 2, up to 2n plus 2 terms we have to write. Now this is greater than or equal to this one by this relation. A1 greater than or equal to earlier term is greater than or equal to the next term, and therefore this quantity is positive, and S2n plus a positive quantity is certainly greater than or equal to S2n. So therefore this is greater than or equal to S2n. Since by A, hypothesis A, A2n plus 1 is greater than or equal to A2n plus 2, and thus we have S2n plus 2 is greater than or equal to S2n, and thus we will have, now see, what is the first term is S2, and if you consider this one, S2 is, so this is a positive quantity we have written. S2n in general, S2n is greater than or equal to S2n plus, see, this is greater, and therefore S2n is less than or equal to S2n plus 2, and therefore we will get the relation as S2 is less than or equal to S4. So this is less than or equal to this one, means earlier term is less than or equal to the next term. S4 is less than or equal to S6, and in general S2n is less than or equal to S2n plus 2, and so on. So this is the relation that we have obtained. Now what about this sequence subsequence S2n plus, whether increasing or decreasing? So here S2, the terms are increasing, and that means this is non-decreasing sequence. See, what about the earlier sequence? We have the relation like this: S1 is greater than or equal to S3 is greater than or equal to S5, and we have written the sequence is non-increasing, and this sequence is non-decreasing. So therefore the sequence the sequence or subsequence S2n, n takes value 1 to infinity. Here also this is a subsequence. So sequence we will consider as Sn, and the subsequence S2n is non-decreasing. Actually increasing, but we use the word non-decreasing. And further, so that is the difference. Earlier sequence we have written, it is non-increasing, and this sequence is non-decreasing sequence. Now again we will consider the general term of this sequence, and that general term is S2n. The sequence is S2n, so also S2n, and that can be written with sum of first two n terms. Start with a1, and then we take negative sign common, and that will be a2 plus a3, and next a4 minus a5. So this must be minus, because odd index terms are positive, even index terms are negative. See, the same expression we are writing like this: a1 minus a2 plus a3 minus a4. Here we have written a1 first as separate, and then we are using brackets minus a2. See, it is minus a2, and a3 is positive plus a3, minus a4, and that a5 will be positive, and so on. So that is minus, and this is continued, and the next terms, last term is a2n, that is this one, a2n even term, and that is negative, and earlier to that term we should write a2n minus 2, and next is a2n minus 1, and next is a2n. So last term, and earlier terms we have written 2n, 2n minus 1, 2n minus 2. You should note this, and see, this is the difference in writing the sum of even index terms and odd index terms. Here we have grouped the terms starting with 1. Here we have separated the first term, and then we are grouping the terms writing minus sign common, and the value remains the same, that of a1 minus a2 plus a3, etc. Even index terms are negative, odd index terms are positive, that we have to remember. And now what happens, so we should use condition A. So a2 is greater than or equal to a3. So a2 is greater than or equal to a3 means this quantity is again non-negative or maybe positive, and this quantity is non-negative, and so on. So last term is positive, actually a2n is positive, and negative sign is separate, but this is numerically positive terms, and therefore this is a1 minus some positive quantity, and therefore that will be certainly less than or equal to a1. So that we shall write, since each quantity, this is less than or equal to a1, since by a, each quantity in brackets is non-negative. Same reason we are writing as we have written earlier, non-negative, and a2n is greater than 0. So therefore this becomes a1 minus some positive quantity. So a1 minus some positive quantity is less than or equal to a1, and therefore s2n is less than equal to a1, and that we have. See here. So therefore s2n is less than or equal to a1, and this happens for all n belongs to n. So what this shows, the terms of the sequence cannot be greater than a1, either equal to a1 or less than a1. That means s2n is bounded above, and therefore this sequence s2n, n takes value 1 to infinity, is bounded above. And now see what we have proved is the sequence is non-decreasing. Subsequence s2n is non-decreasing and bounded above. The sequence is increasing but it is bounded above, and therefore it must be convergent. This is the theorem we have proved in the chapter of sequences, and thus this sequence s2n is bounded. So two results we are using. Earlier we have shown that the sequence s2n minus 1 is non-increasing, but that was bounded below. Non-increasing and bounded below, therefore it is convergent. And this sequence, subsequence of even index is non-decreasing and bounded above, and therefore it is also convergent. Thus s2n is convergent. This sequence is convergent, and thus we have shown both these sequences s2n and s2n minus 1 both are convergent. And now we shall suppose convergent, and its limit of nth term is fixed real number. So we shall suppose these are L and M. Now suppose, so I shall write here, suppose limit n tends to infinity of s2n minus 1 is equal to L. This is a convergent sequence. Suppose it converges to L, and limit, or no need to write bracket, limit of s2n minus 1 is L, and limit n tends to infinity of s2n is equal to M. Both are convergent. They will converge to some real number, that is L and M. And now we will have L minus M, that or M minus M, M minus L is equal to, what is M? It is limit n tends to infinity of s2n minus limit n tends to infinity of s2n minus 1. Or if you take the limit as common to both terms, limit n tends to infinity of s2n minus s2n minus 1. And what is this term? Limit n tends to infinity of, see, s2n minus s2n minus 1. This means sum of first 2n terms, and this means sum of first 2n minus 1 terms, and their subtraction will give the 2nth term only. And what is 2nth term? That is a2n, and therefore this will be a2n. See, s2n minus s2n minus 1. So here it is s2n. These are the terms. And what is s2n minus 1? S2n minus 1 will be the sum of this a2n minus 1 terms, and their subtraction is, actually the term remains as negative, minus a2n will remain. These terms will cancel. So this is s2n, and what is s2n minus 1? S2n minus 1 we will see here, that will be a1, there is no need to write brackets, a1 minus a2 plus a3 and minus so on, and the last is a2n minus 1, that is positive terms, a2n minus 1. So in the subtraction these terms cancel. So this is actually positive, but we have written in bracket, and therefore this the difference of these two will give the last term minus a to n, or we can write here minus a to n. And because of the second condition, you see, limit n tends to infinity, a n is 0, and that means limit n tends to infinity, a to n is also 0, because as n tends to infinity this is going to be 0 and this is equal to 0 by hypothesis B. So by this condition, and thus m minus l is 0 means m is equal to l. So thus m is equal to l. And therefore both these sequences S2n and S2n minus 1 converge to the same limit. Now that we have. Further, what about Sn then? Both this sequence converge to the same limit, S2n and S2n minus 1 converge to the same limit. We want to show Sn converges to the same limit. So if a sequence is convergent, then all its subsequences also converge to the same limit. So, but here we have proved the subsequences are convergent. These two with even index and odd index are converges and converging to the same limit. We will show that Sn also converges to the same limit. So further, by this, since S2n minus 1 limit of see, you can use suppose this as 1. Further, by 1, we use the definition of a limit of a sequence. By 1 there exists for given epsilon greater than 0, there exist n1 and n2. n1 comma n2 belongs to I, the positive integers, are such that I denotes set of positive integers such that this sequence converges to L, means the absolute difference S2n minus 1 minus L is less than epsilon, and for n 2n minus 1 greater than or equal to n1, and S2n minus m is less than epsilon for 2n, this is greater than or equal to n1 for certain natural number n1, and this happens for 2n greater than or equal to n2. This we have used the definition of limit of sequence. Absolute difference of these two is less than epsilon. Similarly here, absolute difference of these two is less than m, because the limit of these sequences are L and m. But if you choose capital N as maximum between n1 and n2, then both these holds. If capital N is equal to maximum of n1 and n2, then from the above inequalities, we have Sn minus L, or see, L is equal to m, and therefore here we can replace this m by L. And now what happens, because m is L, and we will write what is the absolute difference of Sn minus L, that is also less than epsilon for n greater than or equal to capital N, because beyond this n1 and n2 terms, this even odd index terms, difference of odd index term and L, even index term and L, both becomes less than epsilon. Both these inequality hold if n is maximum of n1 and n2, and therefore every term of the sequence and a difference of every term of the sequence and L becomes less than epsilon. So what this shows, Sn also converges to L. So thus Sn converges to L, and thus we have shown the sequence of partial sum converge to limit L, and this shows that the alternating series, this series is convergent. So this proves that the series summation n takes value 1 to infinity minus 1 to the power n plus 1 into an is convergent and converges to L. So thus we have proved the theorem on alternating series, which is important. There are two conditions for convergence of alternating series. First is A1 is greater than or equal to A2, that means this sequence is non-increasing. Sequence AN is non-increasing, and second is limit of nth term is 0, then the series alternating series becomes convergent. Now we will consider an example on this, that is problem on it. For what values of P, the series say it is 1 to the power P minus 1 upon 2 power P plus 1 upon 3 power P and so on. So the first can also be written as 1 upon 1 power P and minus 1 upon 4 power P plus etc. converges. Here for what values of P, and we will consider the case P is less than 0, P is equal to 0 and P is greater than 0. So solution for this first case, let P less than 0, and here if P less than 0 means P is negative. So for that purpose we can consider P as minus m, where m will be greater than 0. It is negative and we are writing it as minus m, then this m must be positive, otherwise it will become negative and negativity becomes positive. So suppose P is say minus 5, then that m is 5, which is greater than 0. So therefore in this case, what is the an here? Here an is 1 upon n power P. Now we have an is 1 upon n power P, and what will be 1 upon n power P? P is minus m, so n to the power minus m, or that this is minus m, m is greater than 0, and this may be written in the form n to the power m. 1 over n to the power minus m is n to the power m, and what is limit of am? Therefore limit m is positive now, you see, limit n tends to infinity of an is equal to limit n tends to infinity of n power m, and that is actually infinity, and this is certainly not equal to 0, and therefore the limit of nth term is not 0 and the series is not convergent. So this series does not converge. So that is the result for P is less than 0. Now we consider the case P equal to 0. Second case, let P equal to 0. The series becomes, in this case, the series is, or the alternating series. If P is 0, see 1 upon 1 to the power 0, that is 1, 2 power 0 is 1, to 3 power 0 is also 1. So each term is 1, but the signs are alternate plus and minus. 1 minus 1 plus 1 minus 1 plus 1, etc. And therefore what is here nth term? Nth term is either plus 1 or minus 1, and therefore here an is minus 1 to the power n plus 1. This is an. So first term is positive, second is negative, and therefore we have written minus 1 to the power n plus 1. And what about limit of an? So limit of an is equal to either if it depends on n is even or odd. If n is odd, then this is n plus 1 is even, and therefore it is plus 1. And if n is even, then n plus 1 is odd, and then it is minus 1. So limit of an is equal to, it is 1 if n is odd, and minus 1 if n is even. So this is the case, and that means certainly limit of an is not 0, and therefore limit of an n tends to infinity of an is not equal to 0, and therefore the series is not convergent. Therefore the series or the given series is not convergent. Now the third case we shall consider p is greater than 0. Case 3, p greater than 0, and in this case we have the series is here. So in this case, what is an? An is 1 power 1 upon n power p. An is 1 over n to the power p. We have n power p is less than n power p plus n plus 1 power p. Since p is greater than 0, n is less than n plus 1, so therefore n power p is less than n plus 1 power p, and taking the reciprocal we will get 1 over n power p, and that will be greater than 1 over n plus 1 power p, or that what is this? This is an, that is an is greater than an plus 1, and this is true for all n belongs to I positive integers, and that means the first condition is satisfied. An is greater than an plus 1. So in this case, therefore A is satisfied. Also, what about limit of an? Also limit n tends to infinity of an is equal to limit n tends to infinity of 1 over n power p. N is see, p is positive and n is also positive. So n is infinity, infinity raised to positive value at denominator, means denominator becomes infinite, and since denominator becomes infinite, the value will tend to 0. So therefore this is 0. For example, we have limit of 1 upon n square, as n tends to infinity tends to 0. So therefore the limit of an is 0. That means the second condition is satisfied. So here both a and b conditions of the theorem are satisfied, and thus this series when p is greater than 0 is convergent. So therefore by theorem 7, the given series is convergent if p is greater than 0. So this is actually the answer. For what values of p the series convergence? The series convergence for p greater than 0. Now what happens if P is 1 in general, or that can be considered as, if P is equal to 1, then the series is, what will be this series? 1 minus 1 by 2 plus 1 by 3 and minus 1 by 4 plus etc. So in this case also the series is convergent, because P is 1 means P is greater than 0, and for this series you see these conditions are satisfied. So A1 is greater than or equal to A2, means 1 is greater than half is greater than 1/3, etc. And what about limit of an? Here the an is 1 by n, and that limit of 1 by n is 0. So therefore the series is convergent. This series is convergent. So thus we have studied alternating series, the meaning or notation for the alternating series, and an important theorem about the convergence of alternating series. If these two conditions are satisfied, then this alternating series is convergent. So remaining part we will continue in our next lecture. Thank you for watching.